If you give a frontier AI agent a highly complex software bug, it might actually just solve it.
Right, yeah, it totally might.
But if you take away the exact error log and just say, like, hey, the app is acting weird, that same multi-billion parameter model completely falls apart.
Oh, absolutely crumbles.
Yeah. So our mission here at AI Paperslop is to cut through the noise, and today we're going straight to the core of this massive July 2026 release. It's called Tencent WorkBuddy Bench, a multi-domain coding agent benchmark with contamination-resistant task construction.
It is a mouthful, but it's so important for where we are right now.
Exactly. I mean, if you are an AI researcher or an ML engineer, you already know the crisis we are facing with agent evaluation.
Yeah, the evaluation trap.
Right. So benchmarks right now basically fall into two bad traps. They are either open source and static, meaning models just memorize the public GitHub issues they were trained on, like in SWE Bench.
Which is, a huge problem.
Or they are closed source and totally unauditable, like Cursor Bench. But Tencent WorkBuddy Bench solves this by evaluating agents across 4 unified domains: code, web, office, and security.
And their secret weapon is this thing they call contamination resistance.
Yes. Instead of scraping raw issues, they reverse engineer historical commits and real CVEs into, like, colloquial role-played requests where the root cause is completely withheld.
Which completely changes the game.
It really does. So over the next few minutes, we are going to explore this fully open source data set and dig into some highly surprising leaderboard results, like how an open weight model absolutely dominates the security track.
That was a huge shock to see, honestly.
I know, right? And we'll look at why the evaluation harness itself is secretly changing model rankings and why spending more tokens definitely doesn't guarantee a higher score. So let's just get right into it.
Yeah, let's do it. I mean, it is exactly the reality check the field has been waiting for.
Yep.
We have been flying blind for a while now, just assuming that if a model crushes a public leaderboard, it will naturally perform well in a real organization.
Which is rarely true.
Exactly.
Yeah.
Enterprise deployment isn't about resolving a single, well-documented bug report. Agents have to reconcile messy spreadsheets, build stateful front ends, and parse, super complex security artifacts.
All at the same time, basically.
Right. And WorkBuddy Bench forces all of those into one unified evaluation boundary. And it does so while directly attacking the core issue of data contamination.
Right, the data contamination problem. I mean, you train a model on the entire internet, and then you test it on a benchmark built from the internet.
It makes no sense.
It really doesn't. Open benchmarks like SW Bench or Web Arena have their problem statements and their solutions just circulating out there on the web.
Literally in the training data.
Yeah. So when a model gets a high score, you don't actually know if it reasoned its way to the answer or if it just regurgitated a memorized solution.
You're just testing its memory at that point.
Exactly. But then you have the alternative, right? Vendor benchmarks, which use real private production sessions to avoid that memorization.
Right, the closed source ones.
Yeah, and because they are private, they are closed source. You can't audit them to see if they just happen to heavily favor the vendor's own agent architecture.
And that leaves ML teams stuck, right?
Yeah.
Choosing between a public test that the model probably memorized
Yeah.
or a private test that you just have to blindly trust.
It's a terrible trade-off.
It really is. What's fascinating here is how Tencent WorkBuddy Bench threads that needle. They build their tasks from real upstream artifacts.
Okay, what kind of artifacts?
Well, they'll take a historical commit, a pull request, or an actual business scenario, but they don't just paste that into the prompt. They completely rewrite it.
Oh, interesting.
Yeah, they withhold the reference diff, meaning the actual lines of code that change to fix the issue are entirely hidden. They don't give the agent the tidy, pre-diagnosed issue title.
So what do they give it instead?
Instead, they create a short, underspecified natural language request from a specific persona, like a product manager or a QA engineer.
Okay, let's unpack this, because this mechanism is what makes the whole paper work.
Yeah, it's the core of it.
It's like testing a student, Current benchmarks basically give the student an open book test where they can just search for the exact wording of the question on Google.
Right, just copy-paste the answer.
Exactly. WorkBuddy is taking real-world problems but translating them into a completely different language, so the student actually has to understand the concept to solve it.
That is a much more accurate way to look at the mechanism, yeah?
Yeah.
They strip away any framing that hands the agent the solution.
So it's pure reasoning.
Exactly. By doing that, the prompt the agent sees is fundamentally unrecoverable by web searching the underlying issue or pull request thread.
Wow, so even if it memorized the repo, it doesn't help?
Right. Even if the model has memorized the entire GitHub repository, it can't easily map the vague symptom to the specific commit it saw during training.
That is brilliant.
And because they use prompt rewriting and strict dataset versioning instead of relying on secrecy, they can release the entire dataset openly.
Oh, so everything is public.
Everything.
Yeah.
The task directories, the Docker images, the evaluation harness is all completely public.
Which is huge. And because they reconstruct these scenarios rather than scraping raw user logs, there is no raw user session data exposed.
Yeah, no privacy issues.
Right. So they bypass all those privacy constraints that usually keep production-based benchmarks locked up.
Exactly.
Anyone listening can just download this and audit it end to end. So, okay, we've established how they are testing to avoid memorization. Now let's dig into exactly what they are testing.
The fun part.
Yeah. The benchmark is broken into 4 domains, and I want to start with code and web.
Okay, let's do code first.
So the code track has 80 tasks. It focuses on repository-level software engineering, testing across 5 requester roles like developer, QA, PM, algorithm engineer, and ops.
Right, a good mix of perspectives.
But here's where it gets really interesting. The paper points out a totally counterintuitive finding. You would think that bug fixing is the bread and butter of a coding agent, right?
You definitely assume that.
But in this benchmark, the bug fix category is actually the hardest category by far. The mean score is an abysmal 0.47 out of 1.
Less than 50%.
Yeah. Why is a standard bug fix completely destroying these frontier models?
Well, because a real-world bug fix requires navigation, and these models are historically evaluated heavily on code synthesis.
Ah, just writing the code, not finding where to write it?
Exactly. Like we talked about with your translation analogy, they withhold the diagnosis. A real-world bug report isn't a neat stack trace pointing to line 42 of a specific file.
No, it's usually just a Slack message complaining.
Right. It's colloquial, like, hey, when I click this specific sequence of buttons, the cart empties.
Yeah, super vague.
Because WorkBuddy Bench withholds the root cause and the error logs, the agent has to explore the repository, find the intermittent fault based on that one-sentence symptom, and then patch it minimally.
Without breaking anything else.
Exactly. When you force a model to do that, it gets completely lost. It will loop on test file edits until it hits a timeout, or it will get disoriented in large multi-module code bases and edit entirely the wrong files.
So it's a navigation failure?
Yes. They are failing to navigate the code base, not failing to write the code itself.
So they just wander aimlessly because they don't have the exact error log handed to them?
Precisely.
But wait, I want to push back on something regarding the scoring for this code track.
Okay, what's that?
The paper says they evaluate the agent's patch using hidden tests. If the tests are hidden, isn't that just a secret benchmark again? Like, I thought you said everything was open source.
That is an important distinction to clarify, actually. Hidden simply means the tests are withheld from the agent's context window during the execution run.
Oh, so the agent just can't see them while it's working.
Right. The agent cannot see the tests while it is actively trying to solve the problem. If it could, it would just overfit its patch to pass those specific assertions without solving the underlying bug.
That makes total sense.
But those hidden tests are fully available in the open dataset release. So for researchers and ML engineers, absolutely nothing is secret.
Got it.
Yeah, you can download the exact tests used to grade the models and see precisely why your agent failed.
Ah, okay. It's hidden from the model during the test, not hidden from us.
Exactly.
All right. So while getting lost in a code base is a failure of navigation, testing an agent in the web domain introduces a completely different bottleneck: statefulness.
Oh yeah, the web crack is brutal.
The web track has 70 tasks focused on front-end GUI generation, and they enforce this strict artifact not chat contract.
Which is a fundamental shift in evaluation, honestly.
Yeah.
The agent must produce a runnable HTML artifact at a declared output path.
So it can't just talk its way out of it.
Nope. If a model writes a beautiful, perfectly reasoned text explanation of how to build the GUI in the chat window, but fails to generate the actual runnable file on disk, it gets a 0.
Ouch.
It forces the agent to actually build the thing. The scoring is rigorous too. They don't just look at the code.
Yeah. What do they use instead?
They use a blend of deterministic rule checks, LLM and vision language model judges to verify the visual semantics, and an active agent judge that literally interacts with the rendered page.
That is wild. And the results completely flip what you might expect. The hardest tasks in the web domain weren't about making the page look pretty, right?
No, the visual design tasks actually scored highly.
Yeah. The models fell apart on stateful interactions. multi-step game flows, page reloads, data persistence, recovering from empty states.
Because emitting plausible-looking HTML is, well, it's easy for a language model.
Yeah, it's just markup.
But closing the front-end engineering loop is much harder. Maintaining consistency between the underlying state source, the visual display, and the final payload after a user interaction requires a continuous thread of logic.
And they just lose the plot.
Yeah, they really struggle to maintain that over long context windows.
Which perfectly transitions us away from traditional software engineering into the absolute real-world mess of the office and security domains.
Oh, the messy domains. I love these.
Yeah. Let's look at Office first. 50 tasks evaluating how agents work with mixed format local files. We're talking Excel, Word, JSON, PDFs.
Real enterprise stuff.
Exactly. The agent has to read these files, extract what it needs, update workbooks, and preserve cross-file consistency.
Which is incredibly hard for AI.
And the scoring here is fascinating. It's like having two bosses reviewing your work.
How so?
Well, you have a strict accountant who runs deterministic rule checks to ensure the math balances. Did you make the file? Does it have the right schema? Are the state transitions correct?
Okay, and the second boss.
And then you have a manager, the LLM judge, who reads your summary to make sure it actually makes sense, evaluating semantic quality based only on the fixed evidence left behind.
It is close to having two bosses, but there is a crucial catch to how they structure it. The strict accountant has absolute veto power.
Oh, really? Veto power.
Yeah. A known issue with using an LLM as a judge is that it can be heavily biased toward its own model family, or it can be easily swayed by a really verbose, confident-sounding answer.
Right, the classic hallucination problem.
WorkBuddy Bench neuters that bias by separating the two scores. The manager, the LLM judge, cannot override a math failure just because the summary was well written.
That is so smart.
It only evaluates binary semantic rubrics based on the fixed post-task evidence, and each task blends the rule score and the judge score with a specific pre-configured weight.
So it keeps the evaluation strictly grounded in reality. That makes sense. Okay, then we hit the security domain.
The toughest one.
60 tasks covering red and blue team workflows, CVE audits, malware analysis, SOC triage. But unlike the Office track, security is scored entirely deterministically inside an isolated Docker container.
There is no LLM judge at all.
Zero.
None.
This raises an important question for the broader field, right? Like, how do you meaningfully evaluate an AI's capability in cybersecurity without relying on another AI's highly subjective, easily fooled opinion?
Because you really can't bluff your way through a hack. Exactly. In security, being close doesn't count. Tencent's answer is that you don't use an AI judge at all. You use a programmatic numeric reward.
Just pure pass or fail on the execution.
Did the agent produce the proof of concept exploit? Did it output the correct YRA rule, the actual classification script used to identify the malware?
Right.
Did the malware analysis extract the right indicators of compromise, like the exact malicious IP address?
But because they completely removed the LLM judge, they had to build this intense 5-layer anti-cheat infrastructure.
Oh yeah, they had to lock it down.
Because if a model doesn't know the answer, it might just randomly guess everything to see if it accidentally triggers the pass condition.
Precisely. If a model doesn't know how to reverse engineer malware, it might just blindly guess every common file path in a loop to see if the grading script gives it a pass.
Just brute forcing the test.
Yeah. So they built these 5 layers to stop that. For example, they have banned literal scanning.
How does that work?
If the task is to find a hidden flag, the agent can't just hard code the flag string it might have memorized from training.
Oh, nice.
Then they have renamed input tests, which ensure the agent is actually parsing the file structure, not just keying off a predictable file name.
That's clever.
They use overlay and tamper tests to catch trailing data manipulation and encoding dependence tests.
And the 5th layer is honestly my favorite, low-weight decoy fields.
Ah, the tripwires.
Yeah. It's like they deliberately left tripwires in the environment. If the model interacts with those decoy fields, the benchmark immediately knows it's just blindly enumerating and guessing.
Not actually reasoning.
Right, and its reward just drops straight to 0.
Exactly. This 5-layer infrastructure forces the agent to actually demonstrate the security capability. It proves the model understands the exploit mechanics rather than just exploiting the evaluation environment itself.
Okay, so we know exactly how the benchmark works now. Let's get to the empirical results. The leaderboard.
The moment of truth.
They tested 7 major models across these 4 domains, and the first big takeaway is that there is no single king of the hill.
No one model rules them all.
Right. Claude Opus 4.8 is incredibly strong. It needs code, web, and Office under the CodeBuddy harness. But GPT 5.5 takes the lead in Office under the Claude Code harness.
Which just validates why we need multi-domain evaluation in the first place,
Yeah.
But the most significant finding in the paper is in the security track.
Yes, GLM 5.2, an open-weight model from Zipoo, absolutely dominates the security track.
Out of nowhere.
It outright beats all the frontier closed models under both harnesses. It scores 76.3% under CodeBuddy and 80.8% under Claude Code. That is a massive win for open source AI.
It really is. It tells us that the capability gap between open weight and closed frontier models is no longer uniform.
It's starting to fragment.
It is highly domain dependent now. GLM 5.2 clearly has a structural or training advantage in the kind of deterministic, highly constrained reasoning required for red and blue team security workflows.
Oh, wait, I want to circle back to something you just touched on. You mentioned different scores for different harnesses.
Oh, this is so important.
The paper runs every model through two different evaluation harnesses, CodeBuddy Code and Claude Code. And the evaluation harness itself actually alters the model rankings.
Yes, and for any ML engineers listening who are building out an evaluation pipeline right now, this might be the most critical takeaway from the entire paper.
More than the scores themselves.
Absolutely. The harness is not a neutral measurement instrument.
So what does this all mean? For anyone listening, this means your internal leaderboard is probably lying to you.
Quite possibly, yeah.
If you are comparing an open weight model against GPT 5.5, but you are forcing them both through a wrapper that was heavily optimized for OpenAI's tool signatures, you aren't measuring raw capability. You're measuring harness compatibility right now.
If we connect this to the bigger picture, you are absolutely right.
Yeah.
The harness is a massive hidden variable.
Just look at the code track results.
All right, GPT 5.5 beats GLM 5.2 when they are both evaluated under CodeBuddy. But if you switch the harness to Claude Code, GLM 5.2 suddenly beats GPT 5.5.
It just flips.
In the security track, they saw an 8.6-point mean shift across models just from swapping the harness.
Why does it shift so much?
Because the harness manages the context window. It handles the caching. It parses the tool signatures, the specific formatting the model uses to call external functions, and it dictates how subagents are spawned.
So it's basically the operating system for the agent.
Exactly. A model that excels in one harness might struggle to format its outputs correctly for another.
Which means picking the quote-unquote best model isn't just about looking at a raw benchmark score. It's about how that specific model interacts with the exact infrastructure and tooling environment you plan to deploy it in.
Spot on.
And that brings us perfectly to token economics, because how a model interacts with this environment directly impacts how much it costs to run.
Token spend is everything in production.
The paper tracks how many tokens these models are spending to arrive at their answers, and the variance is staggering. GPT 5.5 achieves top-tier scores using a minimal output token budget,
How middle?
around 6.9K tokens per run on CodeBuddy.
Wow. It is remarkably efficient at getting to the correct state without meandering.
But then you look at a model like DeepSeek V4 Flash. Under the Claude Code harness, DeepSeek spends 28.6K output tokens.
That's huge.
That is roughly 3.3 times more output than GPT 5.5, but it scored almost 15 points lower.
So it's talking more but doing less.
Exactly. It's burning 3 times the compute to get a worse result.
Because high token spend does not guarantee high-quality reasoning. Often, a massive output token count means the agent is just lost.
It's just spinning its wheels.
Yeah, it is hallucinating, it's getting stuck in endless retry loops, or it is constantly correcting its own syntax errors without actually progressing toward the goal.
Just churning tokens for no reason.
For teams deploying these models in production, where inference compute is a massive line item, token efficiency is just as critical as the raw pass rate. You can't afford an agent that writes a novel every time it gets confused by a vague bug report.
So let's wrap this all up. Tencent WorkBuddy Bench is basically providing a blueprint for the future of agent evaluation.
A much-needed blueprint.
It is contamination-resistant because it completely rewrites the prompts and withholds the diagnosis. It is fully auditable. It covers messy, real-world domains like stateful web interactions and deterministic security tasks.
And it exposes the hidden variables.
Right. It openly exposes how sensitive these models are to the harnesses they run in, and how token efficiency is a massive differentiator.
It sets a completely new standard, honestly. By reverse engineering real artifacts into colloquial requests, they have created a benchmark that actually tests understanding, navigation, and state management rather than just search and retrieval memorization.
Exactly, and it leaves you with something really profound to think about.
What's that?
Well, if prompt reverse engineering, taking a well-documented issue and turning it into a colloquial, underspecified request, is what causes these frontier models to fail so drastically, does this imply that future AI training shouldn't just focus on raw code synthesis?
That is a great point.
Maybe we are optimizing for the entirely wrong bottleneck. Maybe the real challenge of the next decade isn't teaching an AI to write perfect syntax, but teaching it how to translate vague, messy human intent into a concrete engineering plan.
That's the real frontier for sure.
Think about your own internal evaluations. Are you testing your agents on real human vagueness, or are you just feeding them clean data they've already memorized during training? Thanks for tuning in to AI Paperslop, and we'll catch you on the next deep dive.